This is your need to know. This is your need to know.
All right, welcome back, everyone. Ready
Yeah.
for another deep dive.
Always ready to dive in.
Today, we've got a real mix. Black holes, microscopy. Even Newton's laws are getting a second look.
Sounds like we've got a lot to unpack.
We do. We've got articles from Science Advances, Physical Review D, and Nature Communications, Science, Physics World, even a YouTube video from MIT Physics.
Wow, quite the lineup. So where do we even begin?
Well, the goal, as always, is to figure out the so what, Like, why should we care about all this cool science?
Yeah, cutting through the jargon to see how it actually impacts us. I like it.
Exactly. So let's start with something kind of terrifying, but also awesome. Black holes.
All right, bring on the cosmic monsters.
This SciTech Daily article on black hole flares really caught my eye.
Black hole flares, huh? What's the latest?
So basically, the super hot stuff around a black hole, it shifts around, right?
Right.
And that causes these huge X-ray bursts, these flares.
Ah, I see. And what's fascinating here is we can actually see these flares happening thanks to telescopes like NASA's NuSTAR and SWIFT.
That's amazing.
It is. And by studying the light from these flares, how it brightens or dims, we get clues about how the gas is moving around the black hole.
So we're learning about black holes just by watching their, tantrums.
Pretty much. It's like cosmic fireworks giving us a glimpse into these mysterious objects.
Now, speaking of glimpses, the comments on that article, some people were going off about different physics theories based on this research.
Oh, really? Like what?
One person was talking about something called topological vortex theory, and they seemed pretty skeptical of the mainstream explanation.
Interesting, yeah. So that commenter, they were suggesting instead of focusing on particles, we should think about the universe in terms of shapes and how those shapes interact.
Shapes, huh? So instead of tiny balls, it's more like a cosmic geometry puzzle.
Sort of. It's a very complex idea, definitely not universally accepted, but it shows how one article can spark all sorts of debate and different perspectives.
Okay, so from the massive scale of black holes, let's zoom way, way in
Buckle up. Where are we headed?
to the world of the ultra-tiny. This Physics World article on MINFLUX microscopy blew my mind.
MIMFLUX, what's that about?
This tech allows scientists to measure distances smaller than atoms.
Whoa. Wait, smaller than atoms? How is that even possible?
I know, right? It's like having a ruler that can measure the space between the letters in a word.
That's insane. But seriously, how does it work?
Well, normal microscopes, they hit a limit, right? Things get blurry if they're too close together.
Yeah, the Rayleigh limit. It's like trying to read tiny print without your glasses.
Exactly. But MIMFLUX uses this special donut beam of light.
Donut beam.
Yeah. And that allows them to pinpoint the location of molecules with incredible precision.
Wow, so they're basically shining a tiny spotlight on these molecules. That's brilliant.
I know, right? And this could be huge for fields like biology and medicine.
Absolutely. Imagine studying the intricate dance of molecules inside cells, seeing how proteins fold, tracking drug interactions. The possibilities are endless.
It's like opening a whole new window into the microscopic world.
Exactly. And who knows what amazing discoveries await us once we can see with this level of detail.
Okay, hold on tight, because we're about to take a sharp turn into the world of physics and question a law that's been around for centuries.
This sounds intriguing. What law are we talking about?
Newton's first law of motion. This Science Alert article argues we've been misinterpreting it all along.
No way! That's like Physics 101 stuff. What do they mean, misinterpreting?
So it all comes down to one word in the original Latin.
Coquatinous.
Quentinus, huh?
Okay, I'm listening.
It's been translated as unless. Like an object at rest stays at rest unless acted on by a force.
Right, the classic definition. So what's wrong with that?
Well, apparently a better translation is insofar as, and that changes the meaning.
Insofar as, okay, I see where this is going. So it's more about acknowledging that forces are always present in the real world, and the law helps us figure out what those forces are based on how things move.
Exactly. It's not saying forces are absent in some ideal situation. It's more like a tool to understand how forces influence motion.
That's actually a really subtle but important distinction. So instead of an object at rest stays at rest, it's more like we can figure out what forces are acting on an object by observing how its motion changes.
Yes. And this reinterpretation actually highlights Newton's genius even more,
How so?
because it reinforces the idea that the same laws govern both objects here on Earth and those in space.
Right. I see. So it's not just about apples falling from trees, it's about the universal nature of these laws. That's pretty profound.
Right, so from reinterpreting the laws of motion, we're jumping to the cutting edge of tech with this Nature Communications article on spintronics.
Spintronics sounds futuristic. What's that all about?
Basically, it's about using the spin of electrons to carry information.
Okay, break that down for me. What do you mean by spin?
Well, imagine electrons not just as tiny charges, but also like little spinning tops.
Ah, okay, got it. So current electronics use the charge of electrons, like switching a light on or off. And spintronics wants to use the spinning motion for even more control.
Exactly. It's like using the swirling motion of water, clockwise or counterclockwise, to send different signals.
That's pretty cool. So what's this breakthrough they achieved?
They've figured out how to transport spin information over long distances without it decaying.
Wait, hold on. Didn't you say the challenge with spintronics was that this spin information tends to fade out quickly? Like trying to shout a message across a noisy room?
Exactly. But this research found a way around that. They use these things called spatially indirect excitants in a super thin material.
Okay, now you're losing me a bit. What in the world are spatially indirect excitants?
Think of them like pairs of electrons and holes, missing electrons, that are separated but still linked.
Okay, so they're using these separated but linked pairs to carry the spin information.
Yeah. And by carefully designing the material, they were able to suppress the things that usually disrupt the spin. It's like creating a superhighway for the spin to travel on.
Wow, that's incredible. So what could this lead to? I mean, practically speaking.
If they can make it work at room temperature, it could revolutionize electronics. We're talking faster, more energy-efficient devices, maybe even completely new types of devices we haven't even imagined yet.
Now, that's a future I can get excited about. Okay, what else have we got?
All right, time for a detour into the realm of science fiction. Or maybe not. This article from Brighter Side of News is about tachyons.
Tachyons, you mean those hypothetical particles that are supposed to travel faster than light?
The one and only. But there's always been a problem, right?
Yeah, the whole causality issue. If something can travel faster than light, it could potentially travel back in time. And that creates all sorts of paradoxes.
Like the classic grandfather paradox, where you go back in time and accidentally prevent your own birth. Mind-boggling stuff.
Exactly. It throws our whole understanding of cause and effect out the window. So what does this article say? Have they solved the paradox?
That's what they claim. Apparently, some new research has found a way to reconcile tachyons with Einstein's theory of relativity.
Now that would be a game changer. How did they do it?
They used a concept from quantum mechanics called two-state formalism.
Two-state formalism. Okay, I'm all ears.
It's a way of describing a system not just by its initial state, but also by its final state. So instead of just looking at where a tachyon starts, you also consider where it ends up.
Okay, so they're taking into account both the beginning and the end of the tachyon's journey. How does that help with the paradox?
Well, by applying this to tachyons, they suggest that these particles could travel back in time without violating causality.
That's pretty mind-bending. So are they saying time travel is actually possible?
It's still very theoretical. But this research at least opens up the possibility that time travel might not be as paradoxical as we once thought.
Wow, I need a minute to process that. From faster-than-light particles to rewriting the laws of motion, this deep dive is full of surprises.
I know, right? And we're not done yet.
Bring it on. What's next?
Let's get back to the world of quantum computing. This article caught my eye because it's about a major challenge researchers have been trying to overcome: quantum error correction.
Ah, quantum error correction. The Achilles heel of quantum computers.
Exactly. Apparently, Rigetti and Riverlane have achieved real-time error correction, which sounds like a big deal.
It's a huge deal. Qubits, the building blocks of quantum computers, they're super sensitive to their environment. Any little disturbance can cause errors, and those errors can snowball and mess up the whole calculation.
It's like trying to build a house of cards in a hurricane.
Perfect analogy.
Yeah.
So how did they manage to achieve real-time error correction? What's so special about that?
Well, the old way of doing it created a backlog of computations. Slowed things down a lot.
Right, because you had to stop and correct errors before you could continue the calculation.
Exactly. But this new demonstration, They achieve decoding times faster than a microsecond. So they can fix errors practically as they happen.
Wow, so it's like having a spell checker that works in real time as you type. That's incredible. How do they manage that?
It's partly thanks to the speed of superconducting qubits, the kind Rigetti uses. They're super fast, which allows for this rapid feedback.
So they're basically eliminating the error backlog, making quantum computations much more efficient.
Exactly. This could be a giant leap towards building reliable and powerful quantum computers.
It definitely feels like we're witnessing a major breakthrough. Quantum error correction is crucial for unlocking the full potential of quantum computing.
Speaking of unlocking potential, we're about to take a visual journey into the heart of matter.
Oh, where are we going now?
This MIT physics YouTube video, it's all about visualizing the nucleus, the tiny core of an atom.
I love those MIT physics videos. They're so well made.
This one's no exception. They do a great job of showing just how incredibly small the nucleus is.
Yeah, it's mind-boggling. We're talking femtometers, a millionth of a billionth of a meter.
Exactly. And they have this amazing visualization of the proton, made up of constantly shifting quarks and gluons. It's like a miniature universe within the atom itself.
It's crazy to think that everything in the universe, from the smallest particles to the largest stars, is ultimately built from these same fundamental building blocks.
Right. And the video also talks about how even subtle differences in the arrangement of protons and neutrons in the nucleus lead to the incredible diversity of elements we see.
It's like a cosmic Lego set where the same basic bricks can create an infinite variety of structures.
I love that analogy. And it's not just abstract concepts either. The video highlights how different nuclei are used in all sorts of practical applications.
Like what?
Tritium powering exit signs, Meridium-241 in smoke detectors.
Wow, so the study of the nucleus, this incredibly small realm, has a tangible impact on our lives in countless ways.
It really does. And it makes you appreciate how these discoveries, from the vastness of black holes to the tiniest particles, are all interconnected.
It's all part of the same grand story of the universe, and we're just beginning to unravel its secrets.
I can't wait to see what other secrets we uncover as we continue this deep dive.
Yeah, it's amazing.
This is your need to know. This is your need to know. Is your need to know.
And speaking of those tiny particles, that article about carbon and oxygen, it really made me think.
Oh yeah, the one that pointed out oxygen is a gas, but carbon's solid.
Exactly. It highlighted how even though everything's made of the same fundamental stuff, how those building blocks are arranged makes a huge difference.
Right, like imagine if oxygen were solid. We wouldn't be breathing very well.
Not at all. And carbon being solid, that's what allows for complex molecules like DNA and proteins, stuff life's made of.
It's like the universe is playing a giant game of atomic Tetris, creating all these different elements.
Haha, I like that. And remember, that article also touched on practical applications of different nuclei, bringing it back down to Earth.
Yeah, the tritium and exit signs, Meridium and smoke detectors. It's wild how this stuff is all around us.
It really shows how nuclear science, it's not just some abstract thing, it's actually impacting our everyday lives.
Now, going back to that black hole article, that commenter who brought up topological vortex theory, that was pretty out there.
Yeah, they were arguing the universe is more about the interplay of shapes, not individual particles.
Their explanation of the universe is like superposition, deflection, and entanglement of geometric shapes. I gotta admit, I was lost.
It's a very complex concept, not widely accepted, but it's interesting to see different perspectives.
So should we just dismiss it then?
Not necessarily. Science has a history of fringe ideas becoming mainstream. It's about keeping an open mind, right?
True. Even if this theory doesn't pan out, it's cool to see people thinking outside the box.
Absolutely. Who knows, maybe someday we'll be doing a deep dive on groundbreaking discoveries in topological vortex theory. But for now, let's stick to what's been rigorously tested.
Speaking of tested, that commenter also mentioned the cobalt-60 experiment.
Ah, yes. They brought that up while critiquing mainstream physics. It seems they disagree with the commonly accepted interpretation of those results.
They even said, and I quote, "So-called official physics publications stubbornly believe that two sets of cobalt-60 rotating in opposite directions can become two sets of objects that mirror each other.
Strong words.
They went on to say this is a typical case that pseudoscience is rampant and domineering. Do you think there's any validity to their criticism?
It's important to be balanced here. Disagreements happen in science, but the cobalt-60 experiment has been extensively studied, and the results are generally considered valid. This commenter's interpretation, while interesting, isn't widely supported.
They seem very passionate, though, even accusing those publications of spreading pseudoscience and blatantly talking nonsense.
It's great to consider different viewpoints, but remember, science is a process. We're always testing, refining our understanding. Challenging ideas is good, but those challenges need to be based on evidence and solid methodology.
So taking everything with a grain of salt, especially online.
Exactly. We aim to do that here on The Deep Dive, providing a well-informed and engaging exploration of science news.
So back to those breakthroughs we discussed. What are your thoughts on NfLUX microscopy? Where could that lead?
Oh, MFLUX has huge potential to change how we understand biology at the molecular level. Imagine seeing protein folding in action or tracking single molecules within a cell.
Unbelievable detail.
Right. It's not just seeing things clearer, it's measuring distances and interactions between molecules with incredible accuracy. We could gain a level of understanding that was unimaginable before.
Okay, now for the big question. Those tachyons. Time travel. Is it really on the horizon?
Haha, I wouldn't pack your bags for the past just yet. The research is fascinating, but still very theoretical. We're a long way from math equations to actually building a time machine.
But the implications, if it were possible,
Whoa!
it would rewrite our understanding of time and causality, possibly even our place in the universe. Okay, back down to Earth for a minute. That long-distance spin transport discovery, how could that change tech?
Spintronics has the potential to revolutionize electronics. Imagine devices that are crazy fast, use way less energy, and can store tons more information.
Almost sounds too good to be true. What are the roadblocks to making this a reality?
The biggest one is getting it to work at room temperature. Right now, it only works in super cold conditions. Plus, they need to figure out how to build it into practical devices.
But if they crack those challenges, it could be a game changer for everything, from phones to supercomputers.
Absolutely. We might even see new types of devices we can't even conceive of yet. It's a really exciting field.
And quantum error correction. Is that the key to unlocking the full power of quantum computers?
It's definitely a crucial step. Error correction is vital for building reliable, scalable quantum computers that can tackle problems beyond anything classical computers can handle.
What needs to happen next to go from these early demonstrations to fully working, error-corrected quantum computers?
They've got to keep improving the speed and efficiency of those error correction techniques while also scaling up the number of qubits in the computers.
It's like a race against time. The faster they can correct errors, the more complex the calculations they can run.
Exactly. The goal is to reach a point where quantum computers can handle long, difficult computations without those errors piling up and ruining everything.
It sounds incredibly challenging, but also incredibly exciting.
Yeah.
Like we're on the verge of a new era of computing.
It really does feel that way. The pace of progress is amazing, and who knows what breakthroughs are just around the corner.
Before we wrap up, something else from that black hole article struck me.
What was that?
The fact that it was NASA telescopes like NuSTAR and SWIFT that made these discoveries possible.
Right. It highlights how crucial technology is to scientific progress. These telescopes let us see things that would otherwise be invisible. They open up whole new realms of exploration.
It makes you appreciate the brilliant minds who design and operate these instruments. They're giving us a glimpse into the wonders of the cosmos that would have been unimaginable not long ago.
Absolutely. And it makes you wonder, what other amazing tools will we create in the future? What new discoveries await us thanks to those advances?
That's a great question to ponder. And speaking of pondering, I think it's about time to give our listeners some food for thought as we wrap up this deep dive. What's one final takeaway you'd like to leave them with?
Well, I think the most important thing to remember is that science is a journey, not a destination. We're constantly learning, questioning, refining our understanding.
It's not about having all the answers. It's about embracing the unknown and the excitement of discovery.
Exactly. And this deep dive has been a perfect example of that. We've explored everything from massive black holes to the tiniest particles, but each new finding just leads to more questions, more avenues to explore.
It reminds us there's always more to learn, and that pursuit of knowledge is an endless, fascinating adventure.
Couldn't have said it better myself.
So to all our listeners, stay curious, keep exploring, and never stop asking questions. And be sure to join us next time for another deep dive into the most captivating science news out there. It really makes you realize how much we still don't know.
Right. It's humbling, but also incredibly exciting. There's so much more to discover.
And the coolest thing is how these different areas of science, they're all starting to connect. The very big, the very small, the laws of physics, and even the building blocks of life.
It's like we're piecing together this massive puzzle, and each new discovery helps us see the bigger picture.
And as we keep exploring, I bet we'll find even more surprising connections.
Oh, absolutely. Who knows what revolutionary ideas are just waiting to be uncovered?
Well, on that note, I think it's time to wrap up this incredible deep dive.
You know, before we go, I want to leave our listeners with one final thought. We've talked a lot about discoveries and breakthroughs, but science is ultimately a human endeavor.
It's driven by curiosity, passion, this desire to understand the world around us.
Exactly. And it's the scientists, the researchers, the dreamers who are pushing the boundaries, making these discoveries happen.
They're the ones asking the tough questions, challenging the status quo, and paving the way for a better future.
So to all our listeners out there, I encourage you, stay curious, keep exploring, and never lose that sense of wonder.
And if you're inspired by what you've heard today, consider supporting scientific research and education in your own communities.
You never know. Maybe one of you will be the next to make a groundbreaking discovery that changes the world.
What a fantastic message to end on. A huge thank you to our expert for sharing their insights and passion for science.
It's been my pleasure. I always enjoy these deep dives.
And to all our listeners, thank you for joining us on this journey of discovery. Until next time, keep those brains buzzing and those questions coming. We'll catch you on the next deep dive.
This is your need to know.